At 124 light-years from Earth, to the constellation Leo, where an exoplanet called K2-18b is reshaping our expectations about potentially habitable worlds. The most recent data from the James Webb Space Telescope, analyzed by a consortium led by the University of Cambridge and published in the astrophysical journal Letters, reveal the presence in the planet's atmosphere of two molecules, dimethyl sulfide and dimethyl disulfide, that on Earth are produced almost exclusively by living organisms, particularly marine phytoplankton. It is the first time these biosignatures have appeared so clearly in the spectrum of an exoplanet within the habitable zone, and the scientific community regards them as the most promising hint yet of life beyond the solar system. K2-18b is not a brand new discovery. Since Kepler first noted it in 2015, it has been scrutinized by Hubble and numerous ground-based observatories. We know it has 8 times Earth's mass, a diameter 2.5 times our own, and a 32.94-day orbit around a red dwarf star smaller and cooler than the Sun. Despite the star's faintness, the tight distance, only 24 million kilometers, means the planet receives an energy flux similar to Earth's. These characteristics place it in what we call the habitable zone, the region around a star where liquid water could exist. Yet habitable requires much more than a temperature balance. We need atmospheric data, geological clues, and, if we are fortunate, traces of living chemistry. Hubble observations in 2016 to 2017 revealed water vapor, hydrogen, and helium in K2-18b's atmosphere. Theoretical models that followed described a world rich in oceans beneath a hydrogen-dominated gas envelope, a Hycean planet, a term coined in 2021 by Niku Madhusudan's group, blending hydrogen and ocean. Unlike rocky super-Earths or gas giants, a Hycean sub-Neptune could host extremely deep seas, moderate pressure and temperate conditions, providing niches where biochemistry might thrive. The qualitative leap came with JWST. In 2023, using the NIRISS and NIRSpec instruments, the Cambridge team spotted a tentative hint of DMS, the molecule that gives Earth's oceans their salty smell. Caution was essential. The signal barely rose above background noise, but the suspicion motivated a second campaign, this time with MIRI, the mid-infrared module. The new spectrum showed not only stronger DMS but also DMDS, a related compound that strengthens the biological interpretation. Both gases absorb light in the same spectral windows, like two identical instruments resonating at the same frequency, and the estimated concentrations are about 10 parts per million, thousands of times higher than Earth's atmospheric levels. Statistical robustness reaches 3 sigma, equivalent to 99.7% confidence. Practically, there is a 0.3% chance the peak is an illusion. In particle physics and increasingly in astrobiology, the discovery threshold is 5 sigma, so further observations are required to reduce the false positive probability almost to 0. The JWST monitoring cycle scheduled for 2025 to 2026 should provide the necessary sensitivity. Meanwhile, future missions such as ESA's ARIEL probe and later NASA's Habitable Worlds Observatory will contribute complementary data. Prudence, however, is not mere statistical formality. Before attributing DMS and DMDS to living organisms, we must exclude abiotic pathways. In laboratories, researchers are already simulating pressures of 1 kilobar and temperatures between 500 and 800 Kelvin to test whether spontaneous chemical reactions, perhaps driven by a sulfur-rich mantle, could generate the same compounds. Another hypothesis proposes a magma ocean beneath a dense hydrogen atmosphere. In that scenario, exotic volcanic processes might produce organic sulfur without biological help. So far, no abiotic model explains concentrations on the order of tens of parts per million, but experimentation has only begun. Meanwhile, the community is debating whether K2-18b truly is a Hycean world. Recent studies suggest a global ocean capped by high-pressure ice layers may be more plausible. Others envision a mainly rocky planet with a thick atmosphere, but no surface oceans. The density of 3.3 grams per cubic centimeter signals the presence of volatiles, but does not reveal their distribution. Resolving the dilemma requires thermal emission measurements, gas distribution maps, and perhaps detection of seasonal variations betraying climate cycles. So why does DMS attract such attention? Well, on Earth this gas originates almost solely from the breakdown of its precursor, dimethyl sulfoniopropanate, which is released by algae when they die or are grazed by bacteria and zooplankton. DMS then passes from water to air, influences cloud formation, and, closes a biogeochemical cycle linking oceans and atmosphere. Under terrestrial conditions, geological processes just can't synthesize it in significant amounts. The simultaneous presence of DMS and carbon dioxide along with a hydrogen-rich atmosphere actually fits models of marine ecosystems on Hycean planets. Nevertheless, the principle of uniformity, that we extend known physical laws to remote contexts, demands confirmation. What holds on Earth may not hold elsewhere. Media enthusiasm is understandable, but the lesson of Venusian phosphine remains vivid. Back in 2020, a Nature Astronomy paper claimed phosphine detection in Venus's clouds, hinting at biological processes. But subsequent analyses scaled back the signal, showing the spectral peak could be explained by sulfur dioxide and calibration artifacts. That episode really warns us not to confuse preliminary observation with a definitive verdict, and to replicate results with different instruments. The authors of the K2-18b study share this caution. Niku Madhusudan notes that the DMS and DMDS signal is consistent across 3 independent pipelines, that instrumental noise has been modeled meticulously, and that mid-infrared spectroscopy provides a robust cross-check. Yet he himself reiterates that, testing and retesting is the only path from a promising indication to compelling evidence. If confirmed, the picture emerging from K2-18b would be, honestly, revolutionary. It would suggest life is not an isolated geochemical quirk, but a relatively common outcome when favorable circumstances, water, energy, carbon, and sulfur, coexist. It would also imply that sub-Neptunes, which are abundant in our galaxy yet absent in the inner solar system, deserve top priority in the next generation of telescope programs. If, on the other hand, the biological trail proves unfounded, we will still expand our catalog of chemical processes on hydrogen-rich planets. Knowing that volcanism or photolysis can generate large quantities of sulfur gases would help avoid future false positives and, refine target selection criteria. Observationally, JWST will remain the key instrument. Its 6.5-meter optics and platform stability isolate flux variations below 1 part in 10,000, which is, honestly, crucial sensitivity for detecting the faint atmospheric shadows of a planet that, to our eyes, is still just a point of light. Each transit of K2-18b lasts about 6 hours and, multiple transits are required to integrate a meaningful spectral signal. Scheduling observations is therefore a logistical challenge since the telescope must share time among dozens of competitive programs. Ground-based observation will also play a role. With the extreme spectral resolution of high-dispersion spectrographs on large telescopes, astronomers can attempt to separate individual molecular lines from starlight by leveraging the Doppler shift caused by orbital motion. Techniques already used to measure winds on hot giants could, in fact, provide independent estimates of DMS and DMDS abundances. Meanwhile, astrochemistry labs are stress-testing alternative scenarios, In pressure chambers, researchers mix hydrogen, methane, and sulfur compounds, irradiating them with ultraviolet lamps that mimic a red dwarf spectrum. They measure the yield of DMS and DMDS in the absence of life. If these experiments show efficient abiotic synthesis, JWST data interpretation must be revised, but if production rates prove negligible, the biological case gains additional credibility. The bottom line is that we stand at an epistemic crossroads. On one hand, data point to molecules that on Earth we associate unequivocally with life. On the other, experience teaches that the universe is more inventive than we imagine and can generate chemical anomalies by unexpected routes. Distinguishing between these possibilities requires, an integrated approach, multi-band observations, advanced atmospheric modeling, and targeted experimentation. Regardless of the outcome, K2-18b has already played its part. It has demonstrated JWST's power, sharpened spectral retrieval methods, and provided a test bed for defining credible biosignatures. Above all, it reminds us that the search for life beyond the solar system is not fantasy, but a concrete scientific program, driven by measurable parameters, error margins, and verification protocols. In conclusion, the discovery of DMS and DMDS on K2-18b represents the most robust piece so far in the astrobiological mosaic. It is not yet the final tile, but the outline is becoming clearer. In the coming years, with new spectroscopic data, refined models, and interdisciplinary collaboration spanning geophysics to molecular biology, we will learn whether those distant gases are truly the breath of alien phytoplankton, or the spectacular outcome of inorganic chemistry we have not yet imagined. Whatever answer emerges will deliver substantial progress. Either we discover we are not alone, or we better understand how rare and precious life is on our fragile planet.